Okay, so in this third lecture, we're going to cover sections 1.8, 1.9, and 1.10. So let's start in 1.8. Let me share my screen. OneNote. So far we've dealt with equations, and in this section 1.8, we're going to deal with a sort of generalization of these. Hold on, okay. For some reason, I'm working with two screens in my Wacom tablets configured to the other screen, so I have to switch these around. Okay. Okay, so let me share this. Try this again. Okay, so as I said, this is section 1.8, and this is on inequalities, which, as I said, are sort of generalization of equations. So there isn't really an all-encompassing definition of an inequality, but I guess you could say maybe one attempt at an all-encompassing definition is that you have one algebraic expression is less than or equal to another algebraic expression. So for example, you could have something like this, and this would qualify or classify it as an inequality, or you could have, say, I don't know, x squared minus x less than or equal to 2. And this first one would be an example of a linear inequality. And this other one would be an example of a nonlinear inequality. More specifically, I'll put in parentheses, or it's actually a quadratic inequality, because we have, if we can rewrite this as x squared minus x minus 2 is less than or equal to 0. And this right here is quadratic polynomial. So this will be a quadratic inequality. So and the equations we encountered so far generally have a finite number of solutions, one, maybe two solutions. So in the case of a linear inequality, you might have one solution. In the case of a quadratic, or in the case of a linear equation, it might have one solution. In the case of a quadratic equation, you might have at most two solutions. But for inequalities, it's possible to have an infinite number of solutions. And that's something that we're going to concern ourselves with in this section. We're going to try to describe the solution set of inequality. So goals. The goal of this is, I guess, this section is to find solution sets of inequalities. So let's look at, well, first of all, I want to look at linear inequalities, but let's look at some rules for simplifying or combining inequalities, which will help us in describing these inequalities. The solution set to inequalities. So we have here this first rule. It says if you have something A is less than B, so some number less than the other, or one expression less than the other, then you can add another expression to both sides and without affecting the inequality. You can do the same thing with subtraction. If you have a positive number and then you have A is less than B, you can say that A is less than B if and only if C times A is less than or equal to C times B. So you can multiply, and that may or may not help you simplify an inequality. In fact, it will. You can, because multiplication is this dividing, really. So 3, you have to be careful with 3 and 4 right here, because 3 applies only if your algebraic expression or your number C is positive. If it's negative, then you have to reverse the sign here. And so you have to be careful with the distinction between these two rules. The next one, number 5, is that if you have A and B are both positive and A is less than or equal to B, this happens if and only if 1 over A is greater than or equal to 1 over B. So when you take the reciprocal, in some sense, just reversing the inequality. And these are not hard to prove. I can go over the proofs of these on Friday when we meet. The next one is that if you have A is less than B and C is less than D, you can add these inequalities. And the last one is so-called transitivity, which is pretty obvious. If A is less than B and B is less than C, then A is less than or equal to C. So we want to keep these rules in mind when we're simplifying inequalities. So let's look at an example of a linear inequality. So this is example 1 in section 1.8. This is we have 3x minus 9x plus 4, and we want to sketch the solution set. So this will be some subset of the real line. And so I guess I'll just say point this here: sketch solution set. So the first step would be to get x on one side and a number on the other side. So what we can do is we can subtract 9 from both sides. Subtract 9 from both sides, we get negative 6x. It's less than 4. And then, so this is the first step. The next step would be to divide by negative 6, but remember this is now a negative number, so by that one rule we have to reverse the inequality. So if we do that, we get x is greater than 4 over, I should say, negative 6. And then finally, we can simplify this to be, which will, when we simplify this, will be negative 2/3. So right from here, we can get, it's pretty clear what the solution set is. The solution set is the interval. So this is a strict inequality. It's strict, x is greater than negative 2/3, strictly greater. It can't be, we have to rule out x being negative 2/3. That is not allowed. That the inequality, such a value of x will not satisfy the inequality. So the solution set will be this. So it's an interval, it's an infinite interval, and it will consist of everything from negative 2/3 to infinity, but not including those endpoints. And then to graph this, we just copy the real line. And then somewhere around here, we have negative 2/3. We'll put another point on here, or distinguished point 0. And we put a circle here because negative 2/3 is not in the set, but everything after it is. So we'll kind of scribble this in, make it bold the line a bit. Okay, so this is example 1. Let's go to example 2. So this is still a linear inequality, but it's a so-called simultaneous. It's a pair of inequalities, but they can be dealt with similarly. So we have example 2. So this is a pair of inequalities, and we're going to solve them simultaneously. So we have 4 is less than or equal to 4 is less than or equal to 3x minus 2, and that's less than 13. No, this is strict inequality. So this first one right here. Let me fix this. This is right, but this part right here is not strict, because we can have an equation. This equality cannot hold, so this is not strict. So again, we want to express x as being less than and equal to something else. So we got to isolate x. So the first thing to do is add 2 to everything. So we have to add 2 to this inequality, and then we have to add 2 to this inequality. So if we do that, we get 6 is less than or equal to 3x is strictly less than 15. And now we can divide by 3. We get 2x, 2 is less than or equal to x is strictly less than 3. I'm sorry, 5. And then we can get a solution set from this. The solution set will be 2 including 2 up to 5, but not including 5 because of this strict inequality here. And then we can graph this. This is not too bad. So we'll have maybe 0 here, we'll have 2 here, and then we'll have 5 somewhere around here. And we put a solid circle at 2 because we want to include 2, and we put a circle, hollow circle at 5 because we don't want to include that, and then we scribble in here because we want all these points included. And that will we finished that will finish the problem. We just solved the inequality, we found the solution set, and we plotted it. We plotted the solution set. So now let's move on to nonlinear inequalities. These ones are a little bit trickier, but with care and in doing them a few times, and you get used to them. So there's this general procedure right here. It's the guidelines for solving nonlinear inequalities. I'm not going to go through it. You can read it if you want. I'm just going to go right into an example. Let's just not fool around and waste time. Let's go look at an example. That's the best way to learn these, is by examples. So we want to solve this is example 3 in section 1.8 is we want to solve the inequality. So let me actually point up here. Now we did linear inequalities. Now we're going to do nonlinear inequalities. So let me point that out here. So now we're moving on to nonlinear inequalities. So we want to solve the following inequality: x squared minus 5x minus x squared is less than or equal to 5x minus 6. So for the first thing to do is to get everything on one side of the equation and factor. This is why we studied factorization, so we can describe these, so we can solve inequalities and describe their solution sets. So what we're going to do is we're going to add, we'll just do this in 2 steps. So we're going to add negative 5x, so we're going to subtract 5x from both sides. So that will give us this, and now we're going to add 6 to both sides. And then finally, we're going to factor. So we get this. So what this says is that we have this product of 2 numbers. Here's the first number, or the first expression, and here's the other expression. So we have this product of 2 numbers, and it says that it's less than or equal to 0. So we need a little fact here. Actually, 2 facts. So here's like fact A. First one is that a product of two numbers is positive if, or zero, if and only if A and B have the same sign. So they're both positive or they're both negative. And the next fact is that a product of two numbers A and B is less than or equal to 0 if and only if A and B have opposite signs. So one is positive and the other is negative, and that will ensure that the product is negative, overall negative. So this is the fact we're going to need right now, but the other one is also helpful. So this is most pertinent for us now. I think I spelled that right. I'll just put that in question marks. This is the one that pertains to this example. So let me just write this down here. Or what we have is, and that is x minus 2 times x minus 3 is less than or equal to 0. So the way to do this is to the best way to do this is to make a table. So we're going to do, let me just write out the table and I'll explain what all this means. So the zeros of this, or the numbers here, let me actually point this out first. It's clear what numbers make this an equation, the equation true. So it's clear what numbers you need to plug in to make this expression right here equal to 0. And that is x is equal to 2 and x is equal to 3. So if you plug in x is equal to 2, then you get 2 minus 2 is 0, and then this whole product will be 0, and 0 is less than or equal to 0. A number is always less than or equal to itself. So these are like the zeros of the inequality. So these are kind of like zeros. Is maybe not a technical term, but just say like they're the zeros of the inequality. They're also what I like to call the breakpoints. This will help us write out this table that I'll soon do. So these are the breakpoints. So we have the idea is that if you're 2, then you make the equality an equation, or if x is 3, you make the equality an equation. But then you need to worry about what happens to the left and right of 2 and 3. What's going on when x is a little bit smaller than 2, or x is a little bit bigger than 2? So these numbers are going to split the real line. And then we're going to look at what the signs of these factors are when we look at numbers to the left of 2, the right of 2, the left of 3, and the right of 3. So this is the first step. Once you factor this like this, look at those breakpoints. What are the zeros? So maybe I'll write here. They're the zeros / roots of the algebraic expression. That's maybe you can define that as the breakpoints of the inequality. So using that, we can write out this table, and I'll explain how I was able to construct this table based upon these breakpoints. So we have the breakpoints are going to give us the intervals, basically. Like, as I said, we know what happens when x is 2 or 3, but we don't know what happens when x is to the left or the right of 3. So we need these intervals. We need to consider the expression when you evaluate it on these intervals. The interval -infinity to 2. So see, we have this is our one breakpoint here. And then the interval from 2 to 3. So now this is to the right of 3. These are our breakpoints here, and this is the interval where we're considering numbers to the right of 2, but the left of 3. And then the last interval will be 3 to infinity. This is another breakpoint, and this is considering those numbers to the right of 3. We want to look at what happens to the sign of this expression, algebraic expression right here. So here we're going to look at the sign of each factor over these intervals. So we have the sign of x minus 2, the sign of x minus 3, and then the sign of the whole product, the whole algebraic expression. So the best way to do this is just to take a test number, just the simplest number in this so we're going to look at each interval. We're going to go from here, then we'll go here, and then we'll go here, and we're going to take a test point. So I'm going to take a test point from each interval. And then we're going to look at the sign of each factor and then the overall sign of the algebraic expression. So when x is less than, so it's when say when x is 0, that's certainly in this interval here. X is 0 is in this interval. So we'll take our test 0 value of x is 0. When x is 0, this factor right here is -2. So the sign of this on that interval is negative. When you look at when you take the same thing, when you take that same test value, 0, when you plug it into this factor right here, you get -3. So on this interval, the other factor is also negative. So a product of negative numbers will give you a positive number. Okay. Now, so the overall sign will be greater than or equal to 0 of this. So we can know immediately that this interval, we can rule this interval out. This interval right here, we can rule it out because when you take a number from this interval, you get something that does not satisfy the inequality. You get something that's greater than or equal to 0. We want those values of x which make this whole thing less than or equal to 0 or negative, say. So this, we can say right here, not part of the solution set. So right here, this interval. Now let's go to the next interval. So when we have a number between 2 and 3, what happens to the sign of these? Well, if x is just a little bit bigger than 2, then x minus 2 will be positive. So you can just convince yourself that. If you just take 2.5 minus 2 will be 0.5, which is positive. When you plug in 2.5 into x minus 3, you will get negative 0.5, so that's negative. And then when you take the product of those numbers, you'll get something that's negative. And that's exactly what we want. So this will be part of the solution set. Okay, so now what about this last piece here? So when x is a little bit bigger than 3, say it's 4, what happens to the sign of these factors? So when x is 4, x minus 2 will be 2, so that's positive. When x is 4, x minus 3 will be 1, so that's positive, so this is positive. So this is not part of solution set. So from here we can conclude, we can actually now describe the solution set. So the solution set is the values of x for which x minus 2 times x minus 3 is less than or equal to 0 is true. So the values of x for which this inequality holds or is true is 2, 2, 3, and that's it. Oh, sorry, including 2 and 3, because remember, this is not a strict inequality. So we can include those endpoints. So right here, it's less than or equal to 0. So 2 and 3 are certainly going to be included, and then everything between. So that was an example of a nonlinear inequality. And then now we have just, it looks like 2 more inequalities. The next one is an inequality involving a quotient. So inequalities with quotients. So this is example number 5. This is going to be similar. We're going to have to play that same game of looking at signs. It might not be obvious immediately why we have to do that, but it'll become clear once we've simplified this a little bit. So it's gonna reduce back to the same sort of problem we did, where we have to look at a product or of 2 factors, and we have to ask ourselves, when is it positive, when is it negative? We have to look at these breakpoints and everything. So the first step is to move everything on one side of the inequality. So we'll subtract 1 from both sides, and then we're going to combine these fractions. So got to get a common denominator. So this is really like 1 over 1, so we need a common denominator. And that is just going to be 1 minus x. So 1 over 1 becomes 1 over x, 1 minus x over 1 minus x. And now we can combine these, and we'll get, so this, let me just write it. Hold on. What's going on here? So if you combine these, you get 1 plus x, then we have this negative sign, so then we get negative 1. Then we have this negative distribute over the negative x to become plus x. And this will be 1 over 1 minus x, and this will be greater than or equal to 0. And then we can simplify some more to get 2x, so the 1's cancel out, and then the x, this x combines with this x, so we get 2x, and that 2x will be over 1 minus x. So now we want to find the breakpoints. Remember, this is like the roots of this algebraic expression here. So in other words, you're just going to set that equal to 0 and ask yourself, what values of x make this 0? Well, that's pretty clear. A fraction is 0 if and only if the numerator is 0. Well, this 2x is 0 if and only if x is equal to 0. So actually, we don't have breakpoints. We just have, or actually, I'll just put these in parentheses, because at first we didn't know if there were going to be multiple breakpoints, but now it's clear that we only have 1 breakpoint. Or actually, I'm sorry, I made this mistake. It's not just the roots of these, but it's where, I guess it's where you have to look at. We do actually have 1 more breakpoint, and it's x is equal to 1, and that's because this numerator changes signs around 1, or this denominator, I should say. So breakpoints being, it's not quite true that the breakpoints are just the roots of the algebraic expression, because 1 isn't a root of this algebraic expression. It's just, you have to look at the numerator, and you have to ask yourself, where does that change signs? And you have to ask, you have to ask, where does the denominator change signs? Now, it is true that x minus 1 is a root of the denominator. It's not a root of the whole fraction because you can't divide by 0. But if you just look at 1 minus x by itself, 1 is a root. So it is still true in some sense that breakpoints are roots. It'll be, the breakpoints will basically be the roots. So in this example, we have that the breakpoints are the roots of numerator and denominator. So you have to look at the roots of the numerator and the denominator, and those will give you these breakpoints for the inequality. This is the points at which sign changes may or may not occur. So now this will divide the real line into three segments. And I guess I'm not going to go through this because I don't want to spend too much time on this, but if you want, we can go over this example. But this is, at this point, it's just you do the same thing as you did in the other problem. You just set up your table. So you have the intervals. And then you have the intervals being negative infinity to 0. And then you have 0 to 1. And then you have 1 to infinity. And then you have to look at the sign of 2x, the numerator, then the sign of 1 minus x, the denominator. And then you have to look at the sign of the overall algebraic expression, the fraction here. And you have to use this other fact, which I'll put up here, I guess. So we want this to be greater than or equal to 0. So we have some similar facts about fractions. So I guess I'll call this fact C. This will be A over B is greater than or equal to 0 if and only if A and B have same sign. And then you can guess it, A over B is less than or equal to 0 if and only if A and B have opposite signs. So you have that fact that I cited. I think I spelled this wrong. Who cares? That fact that I cited above about products of numbers being positive or negative has an analogous fact for fractions. So using these facts, you just look at this, and I guess I'll just fill in the table and I'll leave it to you to figure out why this is true. But you get a negative here, a plus here, a minus here. Then you get plus, plus, plus. Then you get plus, minus, minus. And this will be clear because we want the overall expression to be positive. This is the solution set. So the solution set will be 0 to 1, not including 1 though, because we can't have division. We can't have division by 0. So that's another subtlety you have to keep in mind. So I won't go over why this is all the case, because it's basically the example that we already did. Well, as I said, if you want to go over it during class on Friday, we can. So the last thing for section 1.8 that I want to go over is absolute value inequalities. So this is another example of nonlinear inequalities. These generally come in pairs. So absolute value inequalities. So let me pull up this table that will be helpful because it gives us some definitions. So this first, so we have a table, it gives you the inequality, it gives you this equivalent form. and then it gives you a plot of the solution set. So this is basically this second column tells you what this first inequality means. So we have the absolute value of x, and remember, absolute value is the size of the number. Basically, it gives you the positive part of the number. So it says the absolute value of x is strictly less than c is the same thing as this pair of inequalities. And then here gives you the plot over here. And then the less than or equal to the absolute value of x less than or equal to c corresponds to this. This is just what that inequality means, and this is a plot. And then you have absolute value of x is greater than c, means is equivalent to these two pairs of inequalities, and the same thing for 4. And these are the plots of them. So I won't write that down, but that's in the book. You can look at that. And so let's look at some examples. So we have example 6, and we're asked to solve the following. Inequality. So this is equivalent. This absolute value inequality is equivalent to this pair of linear inequalities. So it just reduces to a problem that we've already dealt with. And to solve this, so this right here is equivalent to this right here. To solve this, you just isolate x. So we add 5 to both sides. If you do that, you get 3 is less than x is less than 7, and the solution set to this will be 3 to 7, and you can plot that. You get this, so you get 0s here, 3, and then 7 over here. So you put a hollow circle there at each point, 3 and 7, because you don't want to include those, and then you fill in that part. So that's pretty straightforward to solve. The next one is a little bit more tricky. So this is example 7. So example 7 is 3x, the absolute value of 3x plus 2 is greater than or equal to 4. So we have to remember what it means when an absolute value is greater than or equal to a number. So this is equivalent to 3x plus 2 is greater than or equal to 4, or 3x plus 2 is less than or equal to -4. So we have to solve these two pairs. We'll just solve them at the same time. So this absolute value is inequality is equivalent to this, these two pairs of inequalities. So we want, again, just isolate x. So and this first one will subtract 2 from both sides. So we get 3x is greater than or equal to 2. For this one, we want to, again, add or subtract 2 from both sides. So we get 3x is less than or equal to -6. And then in both inequalities, we're going to divide by 2. The first one will get x is greater than or equal to 2/3. And then the other one will get x is less than or equal to -2. Let me just check if I did that right. Kind of went through that fast. Yeah, so this implies that the solution set is a union of two sets. So this is why we care about unions. They're very important operations on sets. So when we say or, that means or should just mean to you that there's a union of two sets is happening. There's going to be some sort of union of two sets, and it's a matter of figuring out. And in this case, you just want to figure out what each set is. So you look at this set. Well, how do I describe this set? Well, this is all the numbers. This is all the numbers. Here, let me get rid of this first. So this first inequality corresponds to the set of all numbers which are greater than or equal to negative 2/3. Okay, so that described set theoretically is as follows. You have 2/3, and you have the square bracket because you want to include 2/3, and then the other endpoint is infinity. And then we have to look at this other set, or this other inequality, and find out the corresponding set. So this is all the numbers less than or equal to negative 2. So you can be anywhere from negative infinity, not including it, because infinity and negative infinity are not numbers, all the way up to negative 2. And as I said, or corresponds to some sort of union, and it's going to just be the union of these two sets. So whenever you see or, you should think union, and when you see and, you should think intersection. So that is all for section 1.8. Okay, so in this, now we're going to move on to section 1.9. So let me share my screen again. So 1.9 is on the coordinate plane. And graphs of equations. So far we have only been thinking about the real line and various subsets of that. Now we want to move on to higher dimensions, although we'll just basically focus on the next step up, which would be 2 dimensions. And we want to think about various subsets of the coordinate plane. So if R is the real line, which is everything between negative infinity and positive infinity, the coordinate plane is this set R squared, which is defined to be R cross R. This is kind of not, it's not really multiplication. So actually, I'll just point that out, not multiplication. Not really. I guess it's some sort of multiplication of sets, but not really. And this just consists of all so-called ordered pairs. So remember, this is how you read this. Is you say that R cross R, R cross R is the set of all these ordered pairs X and Y. So these are ordered pairs slash tuples. We also call them tuples. Such that, remember, this bar right here means such that X is a real number and Y is a real number. So in this case, don't think union or intersection. And doesn't really correspond to, in this case, an intersection, not an intersection. So there's no intersection going on here. We're just expressing the fact that X and Y have to be real numbers. So this, again, R squared is defined to be the set R cross R, which itself is defined to be the set of all ordered pairs or tuples X comma Y, where X and Y are real numbers. And there's a way of representing this geometrically, and it's with a coordinate plane. So that will be, you have these copies of the real line. They're sort of orthogonal to each other. And these ordered pairs give rectangular coordinates. Their coordinates, they give you a position in the plane. So maybe X is some point. So the X, the first number in the ordered pair corresponds to a position along the x-axis. And then the second number corresponds to a position along this y-axis, or this vertical axis. So this vertical axis is called the y-axis. This horizontal axis is called the x-axis. So the point X may be right here. You just draw a line up and say the point Y is here. And then you draw this line here, and then their intersection will be this point X comma Y, point in the plane. And we can talk about points being in quadrants. So in this case, this point is in quadrant 1. We also have over here quadrant 2, quadrant 3, and then quadrant 4. So we're not going to look at just individual points plane, but we're going to look at collections or sets of points. So let's look at some examples of this. So we have example 1 from section 1.9. This is A. So the set we have is the set of all x comma y. So this is a subset of the coordinate plane. It's a subset of r squared. So the set consists of all ordered pairs x comma y such that x is greater than or equal to 0. Now note there's no condition or restriction on y. Y can be anything. So this just says that the x coordinate has to be greater than or equal to 0. And this is not hard to plot. So as I said, this is a subset of r squared. So we can draw it on the coordinate plane. So this is our y-axis. This is our x-axis. And the point x right here corresponds to points along the x-axis. So we're saying x can be any number. It can be 0 and anything positive. Now y can be anything. So what the whole set will be this shaded in region, these two shaded in regions here. So this is the first quadrant, remember, and this is the fourth quadrant. So and includes the y-axis. So it's everything basically to the right of the y-axis. Now let's look at part B. So in this example, we're looking at the set of all x and y such that y is equal to 1. Again, in this case, we don't have a restriction on what x can be. We do have a restriction on what y can be. So what this set is basically consists of all points of the form x comma 1, right? X can be any number where x is just any number, but y has to be 1. So we have to look at where y is 1. So this is the y-axis, this is the x-axis, and say maybe 1 is here. So if you draw this line through here, through that point, you notice that anywhere along this axis, or anywhere along this line right here, your y coordinate is still 1. Your x coordinate is changing because you're moving along parallel to the x-axis, but the y coordinate is not changing. So this right here, this line through the point, so this point right here is 0, 1. The line through 0, 1 that's parallel to the x-axis will be a plot of this set right here. And we can look at this last set. There's one more part to this example, so let's look at this last part. So this is part C. So the set consists of all x, y such that, am I recording? I hope I am. Yes, I'm recording. Okay. So the set consists of all x, y such that, hold on. Okay. So the set consists of all x, y, and y such that the absolute value of x is less than or equal to 1. So again, there's no restriction on or there's no restriction on x can be anything. But remember the definition of an absolute value inequality. This right here is equivalent or is identical to this inequality, this linear inequality. So this corresponds to the interval -1 to 1. So we can draw our coordinate plane. So we have that y-axis, the x-axis. Somewhere here we might have y is 1. So we'll draw a dotted line through it. And then maybe here we have, so this is 1, 0, 1. And then this point right here is 0, -1. So this is y is equal to 1. This is y is equal to -1. And we'll draw a dotted line through this here. Oops. Now, if we consider any point on this dotted line, the y coordinate is forced to be 1 or -1, depending whether it's on this line or this line. But that is a point that won't satisfy this inequality. So we need to keep these dotted lines because we don't want to consider any points on those. But if we're at any point in between them, say these points, the y coordinate will be somewhere between -1 and 1, which is precisely what we need for a point to be in the set. It will satisfy the condition to be in the set. So what that means is that the plot of the set will be this. It will be all this region between these two dotted lines. It will be this horizontal strip. It'll be everything between the two vertical lines, but not including, or anything between the two horizontal lines, but not including them. So the next thing we're going to look at, so in addition to being interested in various subsets of the real line or the coordinate plane, we want to also look at distances between sets, or maybe two sets, or maybe just 2 points. So we have to have a notion of distance. So let's look at that. This is pretty intuitive. The idea is that there's a lot of ways there's actually a lot of ways to measure distance. There's a more general notion of a metric, and it's not the metric, or the way you measure is not always the way it corresponds to what you do on a daily basis. Say, like in the plane, you just look at straight lines. But say you want to measure, say you have a sphere, say you have the Earth or something, which is approximately spherical. It's not actually perfectly spherical, very far from perfectly spherical, actually. But let's just assume, like, spherical cow type of thing. Cows are spherical. Let's just assume that Earth is spherical. If you want to like measure points that are very distant, where the curvature matters, you can't just look at straight lines, because the straight line really won't exist. So you'll have this weird metric. It's this curved metric. Or if you so you won't measure things by straight lines. but the metric will still have some of the same properties that you would like it to have. Even though it won't be your usual notion of distance, it will still have the same properties you would like it to have. For example, the distance between, say, like this is point x and this is point y. The distance between x and y is the same as the distance between y and x. Intuitive, that's exactly what you would want distance to be. And that's what this more general notion of a metric gives you. It gives you this distance. It gives you like a distance function. But you can have some really, really weird spaces, like maybe a sphere, or you can have these so-called hyperbolic spaces. You can look those up just to see how weird spaces can get. Or even in general relativity, which is Einstein's theory, when you have massive objects in space, they deform space-time, and so it changes the way you measure distance because the space-time is being deformed by these massive objects. So distances might become longer. So you have your metric will change depending upon whether it's like this distance between 2 points will change depending upon whether there's a presence of a massive object maybe between the 2 points in space or the 2 observers in space. So it will stretch space-time, and so your usual distance won't work. It will break down basically. So you have to take into account the curvature of space-time itself. But we're not going to worry about that at all. But I just thought I'd point it out that there's these different ways of measuring distance, or there's these different notions of distance, which are encoded in this more general idea of a metric. Not like the metric system that Europeans use or whatever, or the rest of or should I say the rest of the world, but like it's just a distance function. The metric is a distance function. So enough of that though. So what about just distance in the plane? So suppose we have 2 points. If we want the distance to be the usual distance, not some weird curved distance. Let me do it this way actually. So we want it just to be the straight line between them. Well, the idea is that you just use Pythagorean theorem to figure out this distance, the length of this straight line. So we're going to take these 2 points, we're going to draw, dotted lines to them. They're going to intersect the axes, and it'll give us this point that we need right here, which will enable us to measure these distance, and we can use the quadratic formula to get the hypotenuse. So if this point right here is A and this one's B, we could say, and this is actually using this more abstract notation, we can say the metric, or the distance between A and B, is the square root of, well, I need to give labels to these points. So A is x1, y1. So these points are described by ordered pairs. So A is equal to x1, y1, and B is equal to x2, y2. So the distance between A and B is just Pythagorean's theorem, which is the square root of x1 minus x2 squared plus the distance between y1 minus, or just y1 minus y2, which gives you the distance squared. Sorry, that was really messed up. But anyways, so this is just Pythagorean theorem, and I'll give you the length of this hypotenuse here. And that will give you the distance between these 2 points in the plane. So maybe we have, say, A is equal to 1, 2, and then B is equal to, I don't know, say 8, 9. Is that what I want to do? No. So the distance between A and B will be the difference between, so it'll be square root, and then it'll be the difference between the x coordinates, which are 1 and 5, squared, plus the difference between the y coordinates, which will be -2 minus 3 squared. And then that will be, when you simplify that, this will be -4, and then -4 squared gives you 16. And then this will be -2 minus 3, which will give you -5 squared, which will give you 25. And then when you combine these, you get, I don't know, what do you get? 41, I guess. Did I do that right? And this actually can't be simplified any further, but that will be the distance between these 2 points in the plane. So another thing we'll need for when we talk about circles and describing circles with equations is the notion of a midpoint, and that's pretty. I think it's pretty clear once you write it down why this is true, why it holds. So the midpoint from the point A, which is described by these coordinates, x1 and y1, and the other point being x2, y2. So the midpoint is given by this. So you take the average of the x coordinates, so you take x1 plus x2 divided by 2, and then you take the average of the y coordinates. So y1 plus y2 divided by 2. There's some examples, but I'm not going to go over those. Those are pretty easy calculations. That's just a formula I wanted to write down. So now let's look at graphs of equations in 2 variables. Kind of already did this actually. In the first examples, when we had those 3 sets that we described, those are basically equations. Well, the one was an absolute value inequality, but the principle is still the same. So we want to look at graphs of equations in 2 variables. So equations are things like, in 2 variables, something like y minus x squared is equal to 1. And the graph, so this is sort of a definition. The graph of an equation in x and y is the set. So remember, I want to emphasize the importance of sets. That's really all mathematics is, just sets. And functions on sets, which we haven't talked about. But we'll talk about functions eventually. So the graph of an equation in x and y is the set of all points or ordered pairs or tuples x comma y in the coordinate plane, which we denote as r squared, that satisfy the equation that you're given. So for example, if we look at this one right here, 1 comma 1 is a point in the graph because when you plug it in, you get 1 minus 1 squared. No, wait, sorry. That's not right. This is not right. I can't do arithmetic. Hold on. So 1, 0 is a point in the graph because 1 minus 0 squared is equal to 1. So it satisfies the equation. But 1, 1 is not in the graph because 1 minus 1 squared is equal to 0, which is not equal to 1. So it does not satisfy the equation. So you might have a bunch of points that satisfies the equation, and then like the aggregate or the aggregate of all those points will form the graph. So let's see what's so let's write this example down again. So if you example is this, you can rewrite it as y is equal to x squared plus 1. So a point on this plot, the point on this graph will be of the form x comma y, but y is equal to x squared. So you just substitute in what y is. This is y. So these describe all points satisfying, whoops, the equation, and therefore are on the graph. So for example, so there's two ways you can find the points. You can just, you can guess and check. You can say, okay, I'll plug in x equals this, y equals that, and then just figure out whether it satisfies the equation, or you can solve for y. You can't always do this, but you can solve for y, and then just plug in various values of x, and those will give you the right values of y. So you could have x is equal to 0. Let's say x is equal to -1. If x is equal to -1, then y is going to be -1 squared plus 1, which is 2. So this will be a point on the graph. If you plug in 0 for x, y will be 0 squared plus 1. So 0 for x, which is just 1. So this will be a point on the graph. Did I screw something up? No, I did not. And maybe one more point. If you plug in 1 for x, y will be 1 squared plus 1, which is 2. And if you just plug in a bunch of more points for x, you'll find the corresponding y values that satisfy the equation. And if you do that enough times, you'll get a plot. And so the plot's gonna look something like, let me see, it's so it's gonna look something like this. It's gonna look like a parabola, and it opens up at the point 0, 1. Opens up like this. So this is a plot of y is equal to x squared plus 1. So let's see. So the next thing I want to look at is just to quickly look at this absolute value equation. So this is example 6 in 1.9. So this is y is equal to absolute value of x. So you remember what the absolute value is defined as. It's equal to x if x is positive, or so there's some sort of union going on. It's equal to negative x if x is less than or 0. So because we have this or, we have these two cases we can fall under. So if x is positive, then y is equal to x, and xy is a point, or I should say x equals y, which is the same thing as xx, is a point on the graph of this equation. However, if x is less than or equal to 0, then y, by definition, y is going to be equal to negative x. Oops. So this implies that xy is a point which is the same thing as this. So x comma y is the same thing as x comma negative x is a point on the graph. So we have these two things we can plot, and we're in some sense like gluing them together. That's why we have this union. We're kind of gluing the two pieces together. So if you plot y is equal to x, it starts at the origin, and it's this 45-degree angle line. And you can find that just by plugging points in. Always, if you need to, you just go back to the equation, plug points in to figure this out. And the plot of y minus negative x will be this 45-degree angle, or line that's at a 45-degree angle with the negative x-axis, and it goes off like this. And then the whole plot will be this V-shaped thing. This is a plot of this. And how I found it was by plotting the two pieces first. I have these two pieces. This is actually, so remember, I wrote the definition up there, but I'll write it again. It's the absolute value of x is x if x is greater than or equal to 0. It's equal to negative x if x is less than 0. This is an example of a piecewise function, because it has these pieces, these parts. It's a multi-definition function. We haven't talked about function, but this is an example of a function. So the next thing I want to talk about is intercepts. These are important too. For various reasons. I'm not going to really specify them. I mean, they're important in calculus. So you have the intercepts are basically where does the graph cross the axes, the x or the y. So we can define a point as a point. I don't want to say this. I guess the book says it the best way. I won't try to figure out a different way of saying it. So you have x coordinates of the points where a graph of some equation, so you're graphing an equation. So the x coordinate of the points where a graph intersects the x-axis are called x-intercepts. And you obtain them by setting y equal to 0 in the equation and then solving for x. And the same thing can be said of y coordinates. So y coordinates, so this is, let me underline this. This is the definition right here. We're kind of defining what an x-intercept is. And then y coordinates, where a graph, again, of some equation, intersects the y-axis are called y-intercepts. Again, this is a definition of what a y-intercept is, or y-intercepts. And they're obtained by setting x equals 0 in the equation. So just quick geometric illustration of what's going on. So maybe we have some equation, and then this is the corresponding, I don't need to describe what the equation is, but this is the corresponding graph. So we have these points of intersection with the axes. So so we have x-intercepts. That's one right there, that's one right there, and that's one right here. And then we have a single y-intercept. And that's that right there. That's the y-intercept. So let's look at an example. This is example 8. So we have the equation y is equal to x squared minus 2. We can find the x-intercepts. And how we do that is by setting y equal to 0. If we set y equal to 0, we get the equation 0 is equal to x squared minus 2. And if you solve for x, you put 2 on the other side and take the square root, you'll get as x is equal to the square root of plus or minus 2. Those will be the x-intercepts. And the y-intercept is actually just going to be a single y-intercept. The y-intercept is obtained by setting x equal to 0. And when you do that, you get y is equal to 0 squared minus 2, which is just the same thing as y is equal to negative 2. And from these intercepts, you can actually kind of recover the graph. So we know this is a quadratic equation that's y is equal to x squared minus 2. So it's going to kind of look like a parabola of some sort. So this is the y-intercept. So the point in the plane corresponding to this intercept is 0, negative 2. And the points in the plane corresponding to these x-intercepts are square root of 2, 0, and negative square root of 2, 0. So we have maybe negative, the y-intercepts down here, this will be negative 0, or this will be 0, negative 2, and then the x-intercept may be here, and the other one might be here, and this will be the point negative square root of 2, 0, and this will be square root of 2, 0. And then you just kind of open it up like a parabola like this, connect the dots. So just 2 more things I want to cover in this section. And that's equation of a circle. So I'm just going to write down the equation of a circle. You can actually derive it. It's not that difficult, but I won't do that. So we're going to look at the equation of a circle. So this will be a particular type of equation, and we're going to look at its graph. Well, we already know its graph, but I'll just describe the equation of a circle. So the general equation of a circle is the following. So you have an equation of a circle with center h comma k and radius r is given by the following equations: x minus h squared plus y minus k squared is equal to r squared. And then the solution set will be all the x and y that satisfy this. So let's look at some examples. So if you have, so let's let's find the center and radius of the following. So we have the equation is x squared plus y squared is equal to 25. So we want to put it in this form right here, and this will tell us what the center and the radius is. Well, x squared is the same as x minus 0 squared, right? We can add or subtract 0 and it will not affect the equation. And we can do the same thing with y. We could say y squared is the same thing as y minus 0 squared. And then 5, notice the radius comes as this r term over here, which will give us the radius is r squared, and r is the radius. So we want to write this as a square. Well, that's pretty simple. It's just 5 squared. So r is going to be 5, and the center is going to be 0, 0. So this is a circle centered at 0. Now let's look at an example. I won't go over too many examples because maybe we'll go over these on Friday. On Friday, we'll probably do, from section 8, we'll do nonlinear inequalities because those are tricky. And then we'll do equations of circles because these are tricky too. So let's, I won't do too much, but let's do this next one. We want to, this is example 11, and this is, well, we're in this example, we're given an equation, but it's not, and it is a circle, but it's not obviously the equation is a circle. We need to manipulate it a little bit. So show this thing right here represents the equation of some circle. Well, the idea is to use completing the square. And that's why we did this. So completing the square helps you solve quadratic equations, but also this helps you write equations as which don't obviously represent circles into the form of a circle. So we have to use completing the square. So let's put that there in star. We have to do that. Well, we're going to do it for each. We're going to put all the y terms together and all the x terms together, and then the constant term on the other side. So we'll have x squared plus 2x, and then plus y squared minus 6y equals negative 7. So this is a step towards getting something that looks like a circle. And the idea is to do completing the square on this and then completing the square on this. We have to do it twice. So if we look at the first one, we get x squared. Remember, we have the middle, the coefficient of x, we have that, take half of it. We add that in. So we get 2 over 2 squared, and we square it. But then we have to subtract that off. So this line right here is just doing the completing the square on x. Now we're going to do completing the square on all the y stuff, those stuff involving y. So we get y squared minus 6y. Then we have to have the coefficient of y, which is negative 6, square it, and we have to subtract that off, square it, and then we have that negative 7 on the other side. So now on this piece, we can write as a perfect square, and then this piece, hold on, my battery's gonna die. Actually, I think I have enough. I should have enough. So, hold on. Okay, I'm back. Sorry about that. So we can, so as I was saying, this part right here, we can put these together and we can actually do this completing square. So this is 1, and so if you look at this this right here is equal to 1, obviously, because 2 divided by 2 is equal to 1, and then 1 squared is 1. So this is equal to 1. So if you stare at this long enough, you'll see that this just factors as x plus 1 squared. This right here is just going to be minus 1. This piece right here, -2, or -6 divided by 2 will be -3, and then you square that, that'll give you 9. So let me just write under here what this is. It's y squared minus 6y plus 9. Well, it's clear if you stare at this long enough, you'll see that this factors as y minus 3 squared. And then we have this other piece here we have to add on. So this will be minus 9 is equal to -7. So we have x plus 1 squared. The -1 goes with the -9 to give you 10. So you get y minus 3 squared minus 10 is equal to -7. And then we can put this on the other side. We can put the 10 on the other side. So add 10 to both sides to get 3. And then finally, 3 is the same thing as square root of 3 squared, right? So this will tell us that the radius is equal to square root of 3. And the center is, so we got to look at these terms, these numbers here. -1, 3 is the center. Okay, so that was a lot. Okay, first of all, that was a lot of work there. But where we started was something that wasn't obviously a circle, but after going through this completing the square, we obtained this right here, which is the equation of circles. So you have to be careful about what these equations represent. So that's all I want to say for circles. I'll go over those more if you want on Friday. The last thing from what I think we're in 1.9. The last thing from 1.9 is symmetry. So this is a property, this is a geometric property of graphs that can be expressed algebraically. So this is the nice interplay between algebra and geometry, which only gets more beautiful as you go along in mathematics. So let's start with an example. Let's look at this very basic parabola, y is equal to x squared. Let's plot it. It looks something like this. And it's clear that just visually or geometrically, it has a symmetry. It has this symmetry about the y-axis, or with respect to the y-axis. So we have what we have. I mean, this is not a perfect drawing, but we have is that if negative x, well, first of all, if well, we have the graph has this property that if x and y is a point on the graph, then negative x comma y is a point on the graph. So this is called symmetry with respect to the x-axis. So we'll just, I'm going to write down a definition to just give a generalization of this notion of symmetry. And then we'll have two other symmetries that are basically the same. They're similar. So we say, in this case, or more generally, we say a graph of some equation is symmetric with respect to the y-axis if, let's see, I want to be careful about how I say this. If whenever x comma y is a point on the graph, so is x negative x, sorry, comma y. So we say it's symmetric with respect to the y-axis, or maybe also in parentheses about, we might say about the y-axis, if this condition holds, that whenever x and y is a point on the graph, so is negative x comma y. And then we say a graph is symmetric with respect to the x-axis, whoops, if whenever, wait, hold on, yeah, whenever x comma y is a point on the graph, so is x negative y. And then this type of symmetry can be represented like this. This is a sideways parabola. This will be symmetry about the x-axis. And then we have finally symmetry about the origin. So we say we say a graph is symmetric with respect to or about the origin if whenever x comma y is a point on the graph, so is negative x comma negative y. This kind of symmetry, let me see, this is an example of this kind of symmetry right here. Something like this. This will be a symmetry about the origin. And that's all I want to say. That will complete yeah, that will be, and these are very easy the things to test. You just take your equation and you plug in those x's and y's with different signs and see if it satisfies the equation. That'll tell you whether the graph has that symmetry. So that's all I want to say for now. I didn't go over all the examples, but definitely go to the book to look for more examples. And I'll probably go over this more on Friday. So I'm going to stop here because I've been doing this for 2 hours or so straight or something. I don't even remember. Anyways, I'm not going to do 1.9 or 1.10 now. I will do that maybe tomorrow. And so I'll have 2 links. These lectures are going to be meant to go together. So I'm going to stop here now. And I'm going to release the homework in a little bit. So I'll see you Friday.